We're going to be building an LFSR module onto our FPGA on an Accelerate board, and as we do that, we're going to be taking our RTL code, compiling it with Quartus Prime, and using the Arduino IDE to load it onto an Accelerate board. So what that means is the two steps that a person would usually go through to build their own custom FPGA logic, we're going to be taking these two steps, and just as a shortcut, we're going to be building the LFSR module. So I'm actually going to be taking this existing LFSR module that we've written previously and copying it to the Accelerate build directory and building it from there. So, so for anybody that's doing that, all that means is taking the Accelerate LFSR library that's available for free through the Arduino IDE, copying that folder and renaming it to Accelerate build. So an LFSR, or linear feedback shift register, it's just a simple example that we're using. It's a way that you often use to generate pseudo-random numbers. And the particular LFSR that we're doing is just taking an 8-bit data register, and it's grabbing bits 7, 5, 4, and 3 of that data register, shifting the lower 7 bits up by 1, and then appending the result of the XNOR to the lowest bit of the LFSR. So the first thing we're going to do is look at the software implementation of the LFSR. So just quickly, I'm going to open up the Arduino IDE here. So this is the software LFSR example as you would build it in the Arduino IDE. So simple setup and loop in the Arduino sketch. This is the core of the LFSR logic here. So it's just grabbing those bits 7, 5, 4, and 3. And every second it's going to advance the LFSR. So I have an Accelerate board hooked up here on my side. So what I'm going to do is simply load the sketch to the Accelerate board, and then open up a serial monitor so that we can see the output of this sketch. So here we can see the LFSR begins, and every second it's going to work through that LFSR program and output the result of the LFSR. So I just wanted to show you that quickly. That's the standard Arduino way to implement this. And what that's doing in software, as the Arduino IDE compiles that code, it's going to generate the assembly code for that function, and that the assembly code for this LFSR logic looks like this code on the right side of the screen. It ends up being 22 instructions to generate the next number. So that every time you call that function, it steps through these 22 instructions. So I just wanted to demonstrate that and keep that in mind as we go through the rest of this example. So next we're going to look at the hardware implementation for the LFSR. So I'm going to pull up the RTL for the LFSR module, and I'll actually pull that up here in Quartus. So this file is found in the RTL directory of the Accelerate LFSR library. So this here is the totality of the LFSR module. Things to note, we have a new seed signal, an enable signal that controls the flow of the LFSR. So when a new seed comes in, it's going to replace the existing seed with that new seed. And the LFSR is going to advance with that same logic. Here's that same logic that we saw in software, where the The feedback bit is the result of the XNOR of bits 7, 5, 4, and 3 of the LFSR data register. And every time the clock ticks and the LFSR is enabled, it's going to calculate the next state of the LFSR. And one more feature that we have in here is there's a heartbeat signal as an output for the LFSR, and all that is a signal that just toggles high and low, just to show you that the LFSR is moving. So the next thing you want to do is instantiate the source code for our LFSR in our Accelerate wrapper file. And so that's this step here where we have this Accelerate wrapper in the LFSR example. The Accelerate wrapper is called Accelerate LFSR, and all it does is instantiate the LFSR logic and implements the registers for the design. So the LFSR contains 3 registers that control the LFSR. There's the LFSR control register, and all that consists of is 2 bits that users can control the LFSR with. They can set the LFSR into free running mode so that the LFSR will update as fast as it can with every clock tick. If it's not in free running mode, the LFSR is going to advance every time the LFSR data register is read. There's also a heartbeat bit that controls whether or not the heartbeat signal happens at a long interval or a short interval, and that's useful with the free running mode. So the default behavior for the heartbeat is to toggle every 10 advancements of the LFSR. Now, if the clock is running at its full 16 megahertz, a user would never, you would never see the heartbeat toggle. That's not very useful. So by setting that long heartbeat bit in the LFSR control, you can see the heartbeat toggle every 10 million cycles instead. Now, there's also an LFSR seed register, and that register is how the user can write an initial seed state for the LFSR to get the LFSR to start from wherever you want it. And then the LFSR data register is going to be the resulting output of the LFSR module. So just keep in mind that these 3 registers are being used by the design, and we're defining the different addresses for those 3 registers.